So we're going to round off the physics behind magnetic fields by talking about induction before we get back into circuits. So induction is all about how magnetic fields can alter a current in a wire so long as the magnetic field is changing. And so this is all about the work by Michael Faraday. And so we really got to master how electricity and magnetism start to interplay um, with this little section here. So we're going to walk through this process of induction, and this is not like induction in chapter one where we induced charge. This is like a current induction or magnetic induction, where it's magnetic fields that can cause currents. So we're going to have to use this concept of a magnetic flux, which is essentially how much magnetic field goes through an area. And we're going to see these are solenoids, so we're going to talk about how useful they are. Well, in the next chapter, we'll see how useful they are inside of a circuit. So to understand induction, we have this little example here. Just remember, so that if we have a little wire like this, remember that the inside of it is made up of protons and electrons. And we're going to remember that there is a magnetic force, F equals QVB sine theta. And perhaps more importantly, its direction is discussed by the right-hand rule number one, that the velocity and the magnetic field, they're kind of perpendicular to each other, not necessarily, but uh, you can find out what direction that force is, the third vector, as being sort of perpendicular to both velocity and magnetic field. And so this force would be out of the page. And if you're not able to do that on your own, figure out that the force would be out of the page if the velocity is up and the B field is left. Then I would recommend reviewing the chapter previous to this one. So anyways, if we've got this wire of current, it's made up of protons and electrons, and it enters a magnetic field, right? So it's got this velocity going to the right. Something's going to happen, okay? So essentially, even though the wire is neutral, it has the same number of protons as electrons, when it goes through, these charges are going to start to move because they're going to feel a magnetic force. So we can zoom in on the individual sort of atoms and electrons. If you think about a positive charge moving into a magnetic field which is pointing into the page, that's the blue X's, then it should feel an upwards force, But if it was a negative charge, then we would have to flip it and it would feel a downwards force. And so if we realize that these charges are inside of a wire, when the when the current, the wire goes in, like this, it will form a current, by the forces that are moving the charges upwards. This would be like an upwards current, right? All these positive charges would move up, negative would move down, and that would be like an upwards current. Of course, in real life, the protons aren't really doing any of the moving. It's all done by the electrons moving downwards, but that's the same as having an upwards current. Until now, we haven't really paid too much attention to the direction of current, but now we're going to have to start to think about it whenever we're talking about the magnetic field, that there is a direction to the current. Whether it moves up or down is going to matter. Okay, and in this case, these charges, positive charges moving to the right, are going to feel upwards force, and so there will be a sort of upwards current. And so yeah, if you have a wire and it enters a magnetic field, then it is going to create a current in the wire. In general, moving metals nearby magnetic fields can cause currents. Notice that actually, even though this thing was not connected into an entire circuit, you can still have movement of current where the charges inside the metal move around. But let's think about what if we did connect this to a wire loop like this. You know, we don't have to worry about resistors or batteries or anything like that. Even just a little piece of metal in a circle. And let's analyze what happens to the current. We've sort of already decided that this first part, like look at this vertical part, that's what we just sort of analyzed right now. And so if you think of this in steps, as to what's going to happen as it enters this magnetic field, right? Like we're going to pretend that the B is 0 outside of the drawing where the x's are, and then it's into the page where the x's are. Well, we've already decided that the current will be positive, or sorry, upwards in this region as we enter the magnetic field. And so this just entering this metal into the magnetic field will cause an entire flow of current around this loop. It will start going around. If you connected a light bulb, if you put a light bulb over here, for example, it would turn on just by moving it through the magnetic field in this way. Okay, and so now though, we're going to have to look at the right-hand rule as we go through this magnetic field even further. So this is like step 2. Now look at step 3. Once we go a little bit further, so you've got to analyze all the different sizes. So this other vertical part will also feel an upwards current, but that's going to be canceled out by the original upwards current. And so the current is actually going to be there's not going to be a current, a net current in this case. No flow of charge once we're already inside the magnetic field. If you want to think about the top and the bottom side like this, you can do the analysis, but you'll get that it should be an upwards force. And so that's not really going to cause current. I guess it would just cause like the positives to add up on one side of the wire like this and the negatives on the other. They'll bunch up like this. This actually is an important effect, but it's not going to cause any current. I think this is called the Hall effect. And now think about the other side as it plays in reverse. We're going to leave the magnetic field over on this side. Well, there's no more magnetic field to cause a magnetic force, but we still have the left side pushing the current upwards, and so this is going to cause a flow of charges clockwise, opposite to the counterclockwise motion in this first step over here, second step. And finally, once we leave the magnetic field, there will be no flow because there's no magnetic force. So just by looking at QVB sine theta and the right-hand rule, you can see that if you move a loop through a magnetic field, you can cause the flow of currents. And so here's a little summary. You do have to be careful. It seems to matter what orientation these pieces of wire are, and so that is going to be significant. Is sort of what's the relative orientation between the loops and the external magnetic field that is doing the pushing. Okay, and so in general, the most general takeaway here is that currents form in these sort of loops whenever there's a magnetic field and whenever that field is changing, right? Because in this middle step, there was a magnetic field inside, but because it was not changing, then there was no net current. These current pieces canceled out. We need this area where the sort of magnetic field going through this square region has to be changing over time. The magnetic field in that area has to be changing over time. And one more thing to consider here. Look at this step. Let me erase all this again. Look at this first step, or well, first jump, the second step, I guess, here, where the current generated is going counterclockwise this way. We also talked about how currents create a magnetic field, and they do so in a right-hand rule number 2 sort of way. So wrap your fingers around that current loop. Your thumb should be pointing out of the page. This new magnetic field is opposite to the change in the magnetic field that is caused by the external B field. And so this is called Lenz's law. Essentially, the induced current creates an induced magnetic field. Let's call it B induced, which is going to fight the change in the external magnetic field. And so this actually works the other way around as well. We had the wire moving through the wire loop moving through the magnetic field, we can also move the magnet through a wire loop, and it's the same thing. Because we're causing this change in the magnetic field inside of the area, sort of change in the magnetic field in this region, then we can have a current induced and a magnetic field induced uh, in the wire loop. And so uh, we'll do this in the lab on Tuesday, and so yeah, I want to sort of wrap it up real quick here, uh, but first we need to talk about the flux. So this is the last thing here. We won't finish this set of notes right now. I want to talk about the magnetic flux. Okay, so flux is the field times area, and so if you have, for example, here it's really quite easy. If you have an area, you know, this square, let's say it's 1 meter by 1 meter, so 1 meter squared, and you multiply it by the magnetic field inside. So here the magnetic field is constant, and let's say, you know, it was 5 teslas. So 5 teslas in 1 meter, 1 meter. Then B times A would be 5 Tesla meter squared. This would be a quantity known as the magnetic flux. On its own, it's not that important. The magnetic flux by itself, you know, it doesn't really have a strong uh, tangible meaning, but it is useful because we've figured out that if that magnetic flux is changing over time, that's what creates a current. The change in the magnetic flux over time creates a current. Well, this value is going to be equal to is actually going to be called the EMF, which is not a value of current, but this is actually like a voltage. EMF has units of voltage. Okay, and so sometimes it's just curly E, or I like to just write EMF out. It's called electromotive force. It's not a force. I don't know. It's not the best name ever, but the EMF is a voltage created by a change in magnetic flux in a circuit, and that's going to sort of help decide how much voltage, say, would go around a light bulb or going through a resistor or a light bulb or something like that. How much power and current would be going through, it sort of depends. But this would be like an EMF uh, generated across that resistor, a voltage value. And sometimes this is like the backwards voltage. It's generated when the flux changes over time. There's also this minus sign telling you that we fight the change in the magnetic flux. So this can be very complicated. Essentially what it is saying is if you have a loop or an area like this square, and the magnetic field penetrating that area is changing, that's a delta phi, change in magnetic flux, then it will generate a current with an EMF uh, value of like a voltage across. And so this EMF equation is going to be very important. We're going to talk about it on Wednesday, but you're going to use this concept of a change in a magnetic flux in the lab on Tuesday. And so do be careful. EMF is not a force. It's a potential difference with the value in voltage, of volts. And so if there is a change in the flux, then there's an EMF voltage generated. And this voltage drives the current, and so we are going to see that. All right, so we'll finish the rest of these slides later, but for now, take this information to class with you to figure out that first procedure, especially in the lab on Tuesday. All right, I'll see you in class. So real quickly, I wanted to mention a few things about the lab, especially since you didn't have me in person to really guide you through the directionality of the inductive current. So uh, we're going to use this device called a galvanometer. It's actually really quite similar to the ammeter, the device that measures the current, uh, as that we've used before. However, this one can go in two directions, and so This means this is going to allow for us to measure if the current is going backwards than what we would expect it to. And so we're going to move these coils of wire connected to the galvanometer, and we're going to move a magnet inside. And so this is going to be like our wire loops, and this guy is going to be creating our magnetic field. And so it's going to create that magnetic flux through the wire loops, and that's going to cause the galvanometer to activate. The direction at which it activates can be quite difficult, I think, to understand and to predict. Uh, but it's doable. You just have to take it very slow. You got to remember a few things for this lab. So right hand rule number one, let's not forget this one. If you think about very bad finger, V vary is velocity, B bad is the B field, the magnetic field, and F finger is a force. This is going to be our first way to analyze what's happening with the currents as they go through, as the magnetic flux comes in and messes things about. Okay, and then right hand rule number two was where we pointed the thumb in the direction of the current, which kind of like velocity, and we decided that currents create magnetic fields, and they do so in this right hand rule number two way, where the fingers curled around the thumb are the magnetic field. And so this is like where we have the mu naught I over 2 pi r as being the B field created by the current. That's where we use that equation. Okay. Now, we can actually flip this one too. That if we have a set of wire loops, right, in a solenoid, so look at the current is now the thing wrapping around your fingers, and now the magnetic field generated inside is going to go upwards in the direction of your thumb. And so yeah, you can flip right hand rule number two, and it works the same. If you have instead of a straight wire creating a magnetic field, you have a current in a loop creating magnetic fields, then it's going to create one inside, which is pointing upwards in the direction of your thumb. This is the complicated one. This is Lenz's law, which is saying that if you have a change in the magnetic flux, that is to say, paying attention to this gold wire on the left, that if you have a magnetic field that wasn't going through this area and now is, or there was a magnetic field but it's changing, if there's a change in the flux, that means that the area, so the sort of arrows coming out of the magnetic field piercing this this area are changing over time. If this value changes over time, usually by moving the magnet, then that is this change in flux. You can point your thumb in the direction of the change. If, for example, the magnets are getting more northward, more positive, then put your thumb in the direction of this magnet going through the loop. Then your fingers, very annoyingly, will point opposite, because of this negative sign, opposite the direction of the induced current. So if you have a wire loop and you increase the magnetic field this way, it's going to generate a current this way, opposite the right hand rule. Sure, you could use your left hand, but this starts to get very messy. And it also becomes messy when you are, say, entering a south end of a magnetic field, because that one's pointing down. Well, now your thumb has to be pointing downwards as you move your fingers up, and then you have to flip it. It's very complicated. I think it's going to take you dealing with this lab quite slowly and carefully. Don't worry about accuracy. We did not cover enough of this lab, of this material, to worry too much about accuracy here. This is, think of it as an explorative lab. All right. All right, I'll see you there, folks.